Okay, welcome everybody. I'm pleased to introduce today Blanca Osin, I hope I pronounce it correctly, who's assistant professor at the University of Salamanca in Spain for the past 2 years now. And she's going to present a work as a paleoceanographer and micropaleontologist entitled Nannofossil Records in Paleoceanographic Studies from Qualitative to Quantitative. Blanca, firstly, nice to meet you, and I'm really happy to have you today. And it's up to you now.
Okay. Okay, so I think you can see my presentation here. Hello, everyone. I'm very happy to be here and present some of the work I've been doing over the last years, mostly here at Salamanca University, but also at ETH Zurich. And some of this work has only been possible with the help of many collaborators, some of them mentioned here, but of course, there is always many others. I would like to start my talk with a video you've seen already in other NannoTalks. And this is a clip of a cell of Coccolithus pelagicus falsifying coccoliths, right? But while this little critter is doing its homework, I would like you to think about its surroundings. So is it cold? Is it a worm? Is it salty or turbid? Is it nutrient rich or oligotrophic? And how was the CO2? These are very important questions because while this coccolithophore is calcifying calcite clays to build up a cocosphere, it is also meticulously recording all these conditions in both its inorganic and organic components. After the cell dies, the cocosphere disaggregates and some of its remains may fossilize in sediment. This is great news for us, right? Because they provide a precise record of the environmental conditions in which these organisms lived. In other words, coccolithophore ecology is not just that. It is a powerful tool to explore past changes in ocean and climate conditions. So in this talk, I will be showing how we can explore coccolithophore ecology and use it to reconstruct past ocean conditions. Here in this first work, we studied 2 stations that are located in the Northwest Iberian margin, and that is influenced by seasonal upwelling. One coastal station is called Raya. It's 4 kilometers offshore, and it's influenced by coastal processes like river discharges or winter storms. At its location, and then the other station, which is Calibration, which is an offshore station, and it's not influenced by these coastal processes. At its stations, we measure several water properties like temperature or salinity by CTD profiling. And we also sample seawater monthly at different depths along a year. You can see these dots, black dots. These represent each of the water samples we took in order to measure nutrients and also chlorophyll concentrations, but mainly to identify and count coccolithophore attendants. So here are our results. We counted both cocospheres that represents coccolithophore cells and also free coccoliths in the water column. And I will show you now the importance of counting both in order to have a better idea of the ecology of coccolithophores. So at both stations, the number of cocospheres drastically drops below 50 meters water depth. And this is possibly due to rapid zooplankton grazing and also disaggregation of the cocosphere, right, into coccoliths. But at Raya station, we can see that the higher number of cells is observed during the upwelling season. This is a spring or beginning of the summer, but there is also a maximum of the number of coccoliths during the downwelling regime, close to the seafloor, which is 75 meters. Because of the environmental conditions during the downwelling regime are not favorable for coccolithophore growth, and because there are no cocospheres nor other coccoliths over this depth that can explain settling of coccoliths, we believe that they might have been laterally transported from nearby locations or resuspension of coccoliths from underlying sediments. So this observation agrees with the occurrence of coastal processes like stormy events, but also riverine discharges. Consequently, the autochthonous coccolith assemblage here is masked in the water column, and we cannot use this station or the results of this station to explore ecology. However, the story is a bit different in Caliberia. This is the offshore station, where we can see that the highest abundance is modulated by the seasonal upwelling or downwelling regime. Higher abundances are seen during spring, summer, when there is high irradiance levels, as are marked here by these arrows, and also optimal conditions for coccolith for growth. But mostly they occur during warmer waters that are depleted in nutrients, despite being the upwelling season. When we compare the abundance of some of the major species with the water column properties, we can already see some visual correspondence. For example, the small Geophyllocapsa group that you can see here shows two blooms that agree very well with highest chlorophyll concentration. So we could already see that this taxa is indicating higher primary productivity. On the other hand, we can see that Florisfera profunda, at least in Caliberia station, blooms at deeper waters than other species when the nutricline is located at greater depths. Emiliania huxleyi seems to show preference for more stable, warmer, and nutrient-poor waters, but during the upwelling season. So whereas these visual correlations or comparisons are perfectly valid, sometimes they may lead to data misinterpretation. So statistical analysis are very welcome at this stage, just to verify the robustness of our interpretations. For this reason, we perform a CCA, a canonical correspondence analysis, only at Caliberia station. Let's keep in mind that Raya was influenced by coastal processes, masking any relationship of the coccolithophore assemblage with its environment, right? Or at least the environmental conditions we are looking at. On this CCA, environmental variables are represented by arrows. The larger the arrow, the larger the environmental gradient. And then the relationship of each species with the environmental conditions is shown by its relative position in the CCA. The species are marked by black stars. For example, Emiliania huxleyi is linked to the upwelling relaxation conditions. This is, it blooms during the upwelling regime, but mostly related to more stable waters. Let's say when the waters are already warmer and nutrient poor. Okay, but then on the other hand, we can see that a small Geophyllocapsa is also related to the upwelling regime, but to more or colder waters and higher nutrient availability. So despite the common affinity of Emiliania huxleyi and small Geophyllocapsa for the upwelling regime, they seem to have a distinct preference for different stages of the upwelling event. Geophyllocapsa oceanica shows a clear preference for colder, high nutrient waters during the upwelling season. We can see here that it's located very close to these nutrient arrows and also the upwelling index, but very far away or at the other or the opposite sense of the temperature gradient. Conversely, Florisfera profunda shows affinity for the downwelling regime and low productivity conditions. And finally, Syracusfera genus is linked to warmer oligotrophic waters during the non-upwelling season. What is important is that this information on coccolithophore distribution and temporal variations is of great use to qualitatively interpret nanofossil records in terms of past dynamics of the upper water column. And this is something I would like to do in the following work. So here we used over 200 samples from core Shack 065K, located at the classic Shackleton site in the Southwest Iberian margin. It's marked here by this little tiny red star. Apologies for that. And it is densely dated. You can see here all the radiocarbon dates that we produce for this H-depth model that covers the last 28 kiloyears. And this includes the last glacial maximum and all the abrupt events that occurred during the last deglaciation, like Heinrich Stadial 1, Bolin, Alarote, Young Dryas, and so on. We combine nanofossil records with oxygen and carbon stable isotopes, XRF records, and ice rafter debris. I don't want to go into the details regarding paleoclimate reconstructions, but from all the changes we observed, I would like to highlight the importance of nanofossil records to reveal centennial scale oceanographic changes during Heinrich Stadial 2 and 1 that we didn't observe before. So for those that are not familiar with these periods, Heinrich Stadials in the Southwest Iberian margin are cold and arid episodes characterized by the arrival of iceberg melting water, but also the deposition of ice rafter debris. This is mineral grains like the ones that you can see in this sample that can have different colors and sizes, and that have been transported by melting icebergs traveling across the North Atlantic from high to lower latitudes. In the Western Iberian margin, there are several paleoceanographic interpretations during Heinrich Stadials, and they don't agree very well. For instance, high primary productivity has been explained by turbulent mixing produced by these icebergs, or the southward penetration of nutrient-rich waters, or nutrient input by fluvial discharges. But there are other proxy records that for the same period indicate low primary productivity. And this has been explained by other authors due to upwelling weakening linked to a strong surface water stratification. We will see now how coccoliths can help us to unravel this scenario. In our study, we observed that some of the proxy records exhibit a bimodal distribution during both Heinrich Stadials, Heinrich Stadial 2 and Heinrich Stadial 1, and this deserves further attention. For instance, we can see the double peaks in Florisfera profunda lead to decreases in the N ratio. The N ratio is just a proxy for the nutricline depth and is based on the abundance of Florisfera profunda that likes to live at deeper waters, and other primary, coccolithophora species like Emiliania huxleyi and small Geophyllocapsa that live in the upper photic zone. So the higher, or let's say, yes, the higher the N index, the shallower is the nutricline, and the lower, the deepest. And we can see here that there are some periods during Heinrich Stadial 2 and Heinrich Stadial 1 in which we have deepening of the nutricline. This deepening coincides with a higher delta, certain sea excursions marked by red dots as well. And those are interpreted as upwelling weakening, right? So how can we explain this? What we did was to attribute these changes in the nutricline and upwelling strength to the arrival of meltwaters, because fresher surface waters are expected to promote a stronger halocline and suppress wind-induced upwelling and inhibit primary productivity. And this is consistent with the overall low coccolithophore productivity observed for both records, right? However, during the real arrival of icebergs, which is marked by these maxima in ice rafter debris, we observed the opposite scenario. The N index goes up. That means that the nutricline is shallower, and also there is concurrent excursions of the carbon isotopes that indicates higher upwelling or stronger upwelling. So we explain this as the arrival of icebergs producing some mixing. Because coccolithophore productivity is still low, it might be possible that this turbulent mixing during iceberg drift might account for such variations in the nutricline depth and upwelling intensity. Whereas for the coccolithophores, it's difficult to thrive in those conditions, where only a few species like Emiliania huxleyi large or Coccolidus pelagicus would find optimal growth conditions. So given that certain primary producers like dinoflagellates or diatoms can outcompete coccolithophores under medium and high turbulent conditions, the proposed scenario and these centennial scale variations that we find in the Nannofossil records allow us to reconcile previous contrasting productivity interpretations for this study area. So in sum, coccolithophore assemblages are really sensitive to changes in the environment in which they flourish, and thus Nannofossil records are excellent recorders of rapid changes in past environmental conditions. However, there are some assumptions we make in qualitative studies that may introduce important inaccuracies in our interpretations. For instance, we tend to extrapolate environmental affinities, regardless of specific adaptations to environmental changes. Or we base our interpretations in variations of collinear variables, rather than the true variable that it's really controlling the coccolithophore abundance. Or we also use the number of coccoliths rather than the number of coccospheres, because these are rarely preserved in fossil records. Some of these issues can be overcome by using transfer functions that were firstly implemented by Imrie and Kipp in the 70s. And afterwards, they were used by the ClimUp project to reconstruct global sea surface temperature. Since then, this method has been routinely employed in an increasing number of paleoceanographic studies using microfossil census counts. Some of the most used microfossil groups include planktonic foraminifera, from which we can derive temperature, productivity, or sea level, but also diatoms, dinoflagellates, or radiolarians. Coccolithophores too, and this is because they are one of the major components of phytoplankton. However, there are ecological intricacies, and it's difficult for us sometimes to use coccolithophore transfer functions, and for this reason, they have not been systematically employed in paleoceanographic studies. In the following, I want to show you two of our studies that demonstrate the potential of coccolithophores to perform quantitative paleoceanographic reconstructions. But first, what's a transfer function or a climate transfer function? Transfer function is based on the calibration of modern relationships between a specific organism or a specific species with the environmental conditions. Afterwards, this information can be used to reconstruct past environmental variables. A little bit in more detail, this is what we would need to apply or to develop a transfer function. We need a modern training set. This is a calibration data set that has two parts. First, surface sediments or sediment traps from which we can perform census counts, in our case, coccoliths, and also an environmental data set that is contemporary to these samples. And this will be composed of different variables like temperature, salinity, oxygen, nutrient concentrations, and so on. Once we have this training set, we can develop a transfer function, but we need a record to apply it, right? So we also need a fossil data set, which is based on fossil sensors of nanofossils from downcore samples. This would be this part here. Afterwards, we will apply the obtained calibration to this fossil data set in order to reconstruct a specific variables or environmental variables. In this study, I will show you an example for the Western Mediterranean, which is characterized by very strong latitudinal gradients of water properties determined by the entrance of the Atlantic waters through the Strait of Gibraltar. The model training set has two groups of data, as I said before, the coccolithophore species census counts based on mostly or over 90 samples, and then the environmental variables that includes different variables that have been obtained from ocean data view software and averaged annually and seasonally for summer and winter, and selected for different depths. We also use a fossil data set with over 300 downcore samples, to which we will apply the transfer function that we get with our calibration data. But first, we need to explore and calibrate the relationship between coccolithophores and the environment. And the question that arises here is which variable can be reconstructed? For this, we apply a principal component analysis, including all the environmental variables that could explain coccolithophore distribution in the modern training set. You can see the results here. At first, we would need to identify the variables that explain the variance in the coccolithophore training set independently. In other words, we want to exclude collinear variables because they introduce redundant information and complicate the interpretation of the analysis. For example, here we can see that all these gradients are correlated. So for this, we applied a statistical analysis that is called a Kuyke's information criterion that was used to identify the minimum number of variables that, being statistically significant, explain the maximum variation in the modern coccolithophore assemblage. These were salinity, nitrate, phosphate, silicate, and oxygen. But we can only reconstruct one variable, right? So we need to keep looking. And for this, we perform a canonical correspondence analysis, where the vectors show that salinity is the one that exhibits the longest gradient. And also is strongly correlated with CCA1, that indicates a strong relationship with coccolithophore distribution. But still, we don't know which of these variables is the one that is the more important or the most important to explain the variability in our coccolithophore data, right? So for this, we also perform individual CCAs that indicate that salinity is the strongest variable. Because many coccolithophore species thrive within specific ranges of the photic zone and are subject to environmental seasonality, we need to find as well the most suitable calibration. And this is based on the depth and season that most influence the fossil assemblage. So for this, we calculate the amount of downcore variance explained by the summer, winter, and annual salinity reconstructions at 9 different depths. And their statistical significance revealed that the mean annual reconstruction at 10 meters explained the highest variance. And this is the variable that we are going to reconstruct. Annual mean sea surface salinity, sea surface for 10 meters depth. But you might be thinking, is sea surface salinity ecologically plausible? One would expect, or at least us, we're expecting to find nutrient concentration or temperature to be the strongest variable, but we found surface salinity. And statistical results mean very little if they are not supported by true ecological relationships, right? So then we start to dig into literature, and we found that salinity has proven to be important to other marine planktonic groups, such as diatoms or dinoflagellates. And there is plenty of evidence out there for the direct relationship between varying salinities and the morphology of Emiliania huxleyi, not only in surface sediment samples, but also culture experiments. These are some examples, but there are many others that point at the strong influence of salinity on molecular compounds that are produced exclusively by coccolithophores, like alkanones. So here we propose that the assemblage composition may be conditioned by the optimum salinity range preferred by each species. And we must remember that this is a So now that we know that we can significantly reconstruct salinity, we can develop a transfer function. So we use the weight average partial least squares and the modern analog techniques. These are just 2 different models, and we compared both of them. But both methods showed similar quality predictions. They were actually pretty good. R square is between 0.8 and 0.8. 1-to-1 line that indicates perfect prediction. And also the residuals are distributed around 0 and show no apparent pattern. So they indicate that both models show good fit and adequacy. In the end, we end up using the wave average partial least squares to perform our sea surface salinity reconstruction. But the next question that we made ourselves were if this reconstruction was reliable or not. So for this, we applied a principal component analysis to our fossil record, which shows the most important changes in the composition of the fossil coccolithophore assemblage. And we compared with our reconstruction. If the salinity was the variable that was driving coccolithophore variability over this period, then both records should be similar, as we see here in this graph, especially for the last 16 kilo years. They diverge a little bit more for older periods. We also compared our reconstructions with previous records. There are some different resolution in our records compared to previous salinity reconstructions. In general, we see can be used in paleoceanographic interpretations, right? Compared with other proxy records and so on. What we've just shown here is that this regional transfer function that has been implemented in this work could be used to reconstruct sea surface salinity in any core retrieved from the Western Mediterranean and included in paleoclimate reconstruction. The transfer function based on microfossil assemblages are not the only option. There are specific species that show a clear affinity for distinct environmental conditions in relation to their fellows in the same plankton group. This is the case of Florisfera profunda, which I'm sure all of you know. Florisfera profunda is a coccolithophore species that inhabits in the lower photic zone, typically below the depth chlorophyll maximum of the tropical and subtropical oceans. And contrary to the majority of other extant coccolithophore species, high abundances of Florisfera profunda are linked to a deep nutricline. This could be this scenario in which they are all happy and then they bloom because the nutricline is located at deeper position. And then it's related to lower productivity. On the contrary, whenever we have a shallow nutricline, that means high net primary productivity, Florisfera profunda is a little bit sad and prefers not to be there, as depicted here in this beautiful comic by Mariam Saavedra Peliteiro and Ivan Hernandez Almeida. This conceptual model, in which Florisfera profunda only blooms whenever the nutricline is deeper and there is a lower net primary productivity, was applied on surface sediment sample data sets to reconstruct downcore primary productivity, at least here in the low latitude Indian Ocean, by a pioneering work by Luc Beaufort in the 1997, and afterwards by other authors. So these studies were followed by others in different basins, all obtaining quite different calibration or equation calibrations. So we wanted to go global, and we had different aims. The first one was to delimit the current biogeographical distribution of Florisfera profunda in all the oceans. We also wanted to assess the robustness of Florisfera profunda relative abundance and net primary productivity relationships across different oceans or regions. And finally, we wanted to develop a calibration model that allows a quantification at the global scale of net primary productivity changes. We compiled data on Florisfera profunda relative abundance from 1,300, I think, or 250 more or less surface sediment samples and 26 sediment troughs located across a wide latitudinal range in all main oceanic basins. Spatial distribution of Florisfera profunda relative abundance clearly shows decreasing values towards higher latitudes in both hemispheres. Net primary productivity and sea surface salinity are highly correlated to the distribution of Florisfera profunda in surface sediments. And this is because these two variables relate to the position of the nutricline in the case of net primary productivity, or the stratification of the water column in the case of sea surface. But more importantly, their correlation with Florisfera profunda reveals different trends depending on the latitudinal band. Our results show that Florisfera profunda is highly correlated with net primary productivity between 30 degrees north and 30 degrees south, while at higher latitudes shows a higher relationship with temperature. Based on these results, we developed a global calibration model between satellite net primary productivity estimates and Florisfera profunda for this latitudinal band only, the one that is comprised between 30 degrees north and 30 degrees south. And here is our calibration model. The blue line represents the logarithmic regression. The R-square is 0.54, and the gray shaded area shows the residual standard error, which is approximately 0.63. Afterwards, we use Florisfera profunda abundances from 94 sediment cores covering the last glacial maximum. This is from 22 approximately kilo years, but also some of them cover the mid to late Holocene period, which is the last 6,000 years. And with this, we wanted to apply our calibration model and track the past abundance of Florisfera profunda and reconstruct net primary productivity variations. These reconstructions, here you can see the results, shows that net primary productivity was higher during last glacial maximum compared to the mid to late Holocene at low latitudes, increasing carbon fixation and possibly impacting CO2 levels. And this is my last slide, and this is the take-home message that I have for you, that coccolithophores have proven great potential for transfer function development, and although performing qualitative studies is perfectly valid, sometimes sorting to a statistical analysis is good in order to test the robustness of our reconstructions. Existing coccolithophore-based transfer functions, like the ones I've shown before, are very useful tools to reconstruct past oceanographic and climate changes. However, broader understanding of coccolithophore modern, but also past ecologies is still needed to understand some of the relationships we get when we perform a statistical analysis. Now, I would like to thank you all for your attention, and I will be happy to take questions.
Thank you very much, Blanca. It was a great presentation. Is there anybody having a question? Whether you raise hand or you write in the chat. Okay, just waiting a few minutes. Like everybody's clicking on the right button to get online. No, let me just check the hand raising tool here. Okay, so I will start the questions then myself, but I have this, I always ask the same question, so I'm really sorry, I have to ask it. In the first study you showed, you showed the N index, if I remember well, which is, I checked quickly, small placolates and small placolates Florisfera percentage ratio, something like that. And I saw that there were variation between 0.8 and 1 on that ratio. And I wonder how confident are you that you are over any uncertainties in those variations, because it's quite narrow over the total range of the ratio. So do you have any idea on that aspect?
Yeah, I guess the interpretation of this index depends on the location, because, for example, in my region, if we find just 5% of Florisfera profunda, it can be considered a relatively high percentage, let's say. So this will drive very little changes in ratio, but still it's an important change regarding the coccolithophore assemblage. Whereas if we go to other locations where Florisfera profunda can be more abundant, up to 30%, then these variations will be different. And this is why this interpretation of the N index is just qualitatively, and it has to be taken with care, and depending also in the location that we are.
Okay, thank you. Anybody else having a question? No. Please. Mario has a question. So Mario, we listen to you.
Hi all. Well, thank you very much, Blanca. It's great work. I'm full of envy of your work in a good sense. It's a very good approach, and I enjoyed it very, very much. Well, so many questions, but I would like to put you a question that is related with one of the taxa that you mentioned, that is concerning me in general, is that Geophyllocapsa, small Geophyllocapsa and Emiliania, they were plotted in one of your graphs, were plotted nearby, but nevertheless a bit apart. So they more or less mean the same, but not exactly. And one question is that, could that explain, for instance, that we so easily can culture Emiliania axle, and we have very, very few data from cultures for the small Geophyllocapsa, for instance. They should, I mean, they should behave more or less the same in cultures, and we should have a lot of information about the small Geophyllocapsa as we have for Emiliania, but we don't. I mean, we have a lot from Emiliania, especially from biologists. They like it very much. But the small Geophyllocapsa that from our record should be more or less similar, well, things don't happen the same way. Do you have an idea why? You have a feeling about it?
Well, first, I think that people that work culturing Emiliania Huxley does it so easily because others did it before, right? So we just keep doing what the others did. And but then on the other hand, what you said about their specific or different preferences during the upwelling season might be related to that. What I could see, not only by visual comparison of my coccolithophore assemblages with the environmental data set, but also by a statistical analysis, is that both of them like the upwelling season, right? But they're a little bit different, because Emiliania Huxley likes to be there when the waters are already a little bit more warmer and stable. That could be the end of the upwelling period. Let's remember that my sampling period is just 1 day. We went there, we took one sample, and then we came back. So it's the upwelling season, but still, it could be a period in which it's already relaxed. And then for the small Geophyllocapsa group, what we saw is that they also like the upwelling season, but when there were more nutrients and it was more active. And we could also see, I didn't show it here, that we could also see diatoms in the assemblage. While whenever we found Emiliania Huxley, there were not many diatoms because the waters were already a little bit more stratified. So there are distinct ecological preferences that we could distinguish with this statistical analysis, but I cannot give you an answer for your question about cultures. I guess maybe people should try with different levels of nutrients, for example, and also colder temperatures.
Okay, thanks. Thanks so much.
Okay, we have a question in the chat from Laura Bronzo, who asked, what about reworked species? Did you saw some variations?
You mean in the seawater samples or in fossil records?
Laura.
Yeah, I'm asking Laura. Sorry. Fossil record. Yes, we did. I'm not sure if I show it here. Let me just go back to my presentation.
You are still hosting, so that's fine. Yeah.
Okay, let me go back. I just want to see if I show it here in this graph. Yeah, so rework the specimens. What I usually find, especially in this region, in the Southwest Iberian margin, is that they become more abundant in the nanofossil assemblage during Cambridge stadials. And this has been attributed to lateral transport by intermediate nepheloid layers during these periods, because the intermediate nepheloid layer was a little bit deeper, and then it was raining these laterally transported particles over our side. So what you see here, this gray line, is the relative abundance, whereas what you see here in the dark gray or solid gray plot is the absolute abundance. So absolute abundance is higher during the last glacial maximum, but they become more important, or they represent a higher percentage during Cambridge stadials. And well, we attribute it to this, but this is not our idea. Let's say there are other works. I think the author is Ferrero, maybe 2008, that this is a very beautiful study in which they show that the reworked nanofossils in the Gulf of Cadiz come from redistribution of sediments. And then these assemblages here must be taken with caution, because we may find high percentage of reworked nanofossils that don't belong to the region and therefore are alloctonous components of the sediment.
Any other questions? Oh, excuse me. Yeah, any other questions? I do have one, another one, sorry. Martha Martinez has a question about me, so you go first. Okay, just, yeah.
I don't know if you can see me. Hello to everyone, and thank you, Blanca, for your presentation. I celebrated the path from qualitative to quantitative, you know. Maybe you say something about that, but I have a question about the coccolith assemblages. You use the modern nutrient concentration to reconstruct the past water conditions, but it's a question, you know, but there are any study where the modern coccolithophores are collected or in the Gulf of Cadiz, because it could be possible. I don't know if there are something there.
You mean
compare,
from the
you know,
seawater, right?
Yes, modern water.
Yeah, so usually for the calibration data set, we use surface sediments, because this is what most of us do, right? We work with sediments, and it's very rare that we can find seawater samples with also the measurement of the environmental or all the environmental variables that we want. Imagine that we go on a cruise, and then we take some seawater samples. I could measure nutrients, I could measure temperature and salinity, but what about all the others? What about alkalinity, pH, and so on? Sometimes we miss this information. in the last work that I show you by Ivan Hernandez Almeida, nevertheless, we also used some data from sediment traps. And that means collection of coccolids that were traveling in the water. And for this, rather than in situ measurements of these properties, we use satellite measurements that were averaged for the periods of the sediment traps. So this might be a little bit difficult, and you need to be really like working on the data sets a lot, because you need to find the period and also to average it for that period, also the water depth and so on, and it takes a little bit more work, but it's possible. But in general, I would say that all of us work with surface sediments.
Yeah, I know that you are making a good job, but I have that question because I have some sample of water, but I will write you, But thank you for your presentation, Blanca.
Thanks, Marta.
Sorry. Yeah, thank you very much. Is there any other questions? Otherwise, I will ask mine. Actually, when you were showing us the, it was the 2015 work you showed us, I guess, on the salinity, and you show the different parameters and change between the seasons. If I remember well, you were winter and summer, and only I had the feeling that only the salinity was stable during the whole year. How does that affect the fact that maybe, is it because it's that stable that you have the salinity that is significant in your calculation at the end?
Yeah, that could be a possible reason. This is something we explain in the article. And it's not only that there is evidence for the relationship of coccolithophores with salinity, but also because our study site is a little bit special in this way. It's in the Western Mediterranean, where salinity is very important. The hydrological budget in this semi-enclosed basin is negative. That means that there is more evaporation than precipitation, and therefore salinity is really, really important, much more than other variables. And as I show you in these gradients, it varies very little. So it might be that salinity's this annual salinity gradient is overprinting seasonal variations in other variables that are also affecting the coccolithophore assemblage. But in the end, what we really want is to find a variable that explains the majority of variation in our coccolithophore data. And with this, I mean that that we could use this transfer function in the Western Mediterranean, but outside it might not make sense. I mean, first, we could not use it because there is not a calibration data set that includes other sites. But even if we could do the same in other regions, I don't think we would find salinity to be the most important variable driving variance in the coccolithophore data.
Okay, thank you very much. Sorry, anybody else having a question then? Please feel free to ask all the questions you want. And okay, so I guess we have no more questions. So I would like to thank very much Blanca for the very nice presentation she made today, and for accepting, of course, to do this presentation through NannoTalks. Congratulations to you. I would like to thank everybody for coming to those NannoTalks, and I would like to say that next one will be in December, mid-December. Just give me 1 sec on the date that we have picked. Just I checked earlier, I forget. It will be by Rosie Sheward, and it would be, I don't remember the date. We will send it by email. I think it's the 14th of December, and her talk is entitled "Coccolithophore under Climate Change." That's it. I cannot tell more about that. So it will be in about a month, and I guess that's it. Thank you very much, Blanca. And I hope to see you next month in the next NannoTalk. Thank you, everybody. I wish you everybody good evening, morning, whatever, wherever you are. Thanks.
Thank you and bye. Bye-bye.